Let me welcome you to this lecture. We have now looked at different symmetry elements, as well as we have also deduced different kinds of symmetry operations generated by these elements of symmetry. And what we have noticed is that while in case of the plane of symmetry as well as in case of the center of symmetry, only one symmetry operation is generated by each of these elements of symmetry. In case of the proper axis of symmetry as well as in case of the improper axis of symmetry, the number of symmetry operations depend upon the order of the axis essentially, while in case of the proper axis of symmetry we see that both the the odd order axis as well as for even order axis, the C and N operation, that is when we carry out the Cn operation n times, is equal to the identity operation, but that is not the case in case of the improper axis of symmetry. So when n is an even number, then S and N is equal to identity, but when n is an odd number, S and 2n is only equal to identity. So now what we will do is that we will look at all kinds of symmetry operations that are present in a tetrahedral molecule. We have already looked at the kind of plane of symmetry present in a tetrahedral molecule, as well as we have also looked at the proper axis of symmetry, that is how many C3 axes of symmetry are present in tetrahedral molecule. But then apart from that, there are other proper axes of symmetry as well as there are improper axes of symmetry present in the tetrahedral molecule, and we will identify these elements of symmetry and also deduce the number of symmetry operations generated by these symmetry elements in a tetrahedral molecule. So let us begin and let us stick to the same methane molecule that we have taken as example earlier as well. So that is the methane molecule, that is CH4, and what we have already deduced is that there are 6 planes of symmetry are present in tetrahedral molecule, and each of these plane of symmetry produce one operation. That is, there are total 6 sigma operations are present in tetrahedral molecules. There are no center of symmetry in case of the tetrahedral molecule, but then we have found out that there are 4 C3 axes of symmetry are present in the tetrahedral molecule, and each of these C3 axes of symmetry produces 2 symmetry operations, C3-1 and C3-2. So total there are 8 C3 operations are present in the tetrahedral molecule. Now let us see whether any other proper axes of symmetry are present in case of the tetrahedral molecule. Now if we draw the tetrahedral molecule in this fashion, that is, if we put 2 of the hydrogen atom on the plane of the board, while if we place 2 of the hydrogen atoms on a plane which is perpendicular to the plane of the board, and we can draw the tetrahedral molecule in this way already. So then this particular axis which bisects this ACH angle, this one, as well as the ACH angle at the bottom over here, this particular axis, if we do rotation of 180 degree with respect to this axis, so we do a C2 operation with respect to this symmetry axis, then the result, if we write H1, H2, H3 and H4, so if you label them as this, what we are going to get that H1 will be swapped with H4, while H2 will be swapped with H3 in this way. So we arrive at an indistinguishable configuration, and that is why we have performed a symmetry operation, that is a C2 operation we have performed in this case. So there we could identify at least one C2 axis of symmetry in case of the tetrahedron. But then again, as in case of the plane of symmetry, we realize that because the hydrogen atoms here are all equivalent in nature, and that is what allowed us to identify all the plane of symmetry. There is 6 plane of symmetry in case of the tetrahedron. This would also you know let us think that there may be some other C2 axis of symmetry as well, because this C2 axis of symmetry bisects the angle between two sets of hydrogen atoms in the tetrahedral molecule, and that is why if we bisect the angle between the other sets of hydrogen atom, if there are C2 axes passing through these points or not. So in order to visualize that, the best will be if we draw the tetrahedron inside a cube. So let us draw the tetrahedron inside a cube once again. We have learned that if we place the hydrogen atoms at the alternate corners of the cube and the carbon atom at the center of the cube, then the geometry we get is a tetrahedral geometry. So let's also label the hydrogen atoms as H1. So this is H2. This is H3 and then H4. Now the C2 axis, that is, we can visualize that this axis which passes through the carbon atom and it passes through the center of this plane that is on top of the cube over here. If you follow my fingers here, this particular plane, this axis passes through the center of this plane, and then it goes out through the center of the plane which is exactly below this top plane over here, that is this particular plane. So the axis passes through the center of this plane, and in that process the axis will also pass through the carbon atom over here, and what we can see is that this axis now bisects the angle between H1C H4 as well as H2C H3. So when we do C2 operation with respect to this axis, let us label this axis as C2Y, say, because it points, if we take the Cartesian coordinate reference in this way, X, Y, and then Z, then this C2 axis will be, if we place the origin at the carbon atom, this axis will be collinear with the y-axis in the coordinate system over here. So when we do C2y operation, let us draw the final configuration with the tetrahedron here. So what will happen is that H1, once we do C2 rotation with respect to this axis over here, H1 will reach the position of H4, while H4 will reach the position of H1. Similarly, H2 will reach the position of H3, H3 will go to the position of H1. So what we can write is, we can redraw the tetrahedron here. And this is H4 now, this is H1, this is H3, and this is H2. So what we see is that we reach an indistinguishable configuration when we do C2 operation with respect to this C2y axis of symmetry. So this is a symmetry operation, and this is a C2 axis of symmetry passes through this particular point in the tetrahedron. Now, if there are 6 opposite faces in a cube, and if we take this particular face, that is side-on face, and pass an axis through the center of this face, take it through the carbon atom, it will come out through the cube, through this face, that is this particular face over here, it will pass out through the center of this face. And if we do now C2 operation with respect to, or rotate the molecule 180 degree with respect to this particular axis, then this is C2 X operation, because this axis is collinear to the x-axis, and in that case H3 will be now swapped with H4, while H1 will be swapped with H2. So the levels on the hydrogen atoms are going to change. H2 will come over here, while H1 will be there, and then H4 and H3 is going to be there. So this is how again we reach an indistinguishable configuration, except for the level of the hydrogen atom. We cannot distinguish the initial and the final configuration over here. And again, this is a C2 axis of symmetry in the tetrahedral molecule. Then we are left with another opposite faces of the cube, that is the front face over here, and the opposite face is this one over there. And then if we take an axis which passes through the center of the top face over here facing us, as well as the bottom face over there, if the axis goes out of the bottom face, center of the bottom face, and it will pass through the carbon atom once again. And in that case, if we do, that is because this axis is collinear to the z-axis. Now if we do rotation of 180 degree, the final configuration once again we can write, because now H1 and H3 are going to get replaced, are going to be swapped, while H4 and H2 are going to be swapped. So then H3, H1, while H2 and H4. This is the final configuration, which is again indistinguishable from the initial configuration, and we again have performed a C2 operation with respect to this C2 Z axis of symmetry. So what we have found here is that there are three C2 axes of symmetry in the tetrahedral molecule, which bisects the angle between opposite HCH angles essentially. And if we place the tetrahedron inside the cube, then these axes are easy to be visualized because they passes through the opposite center of the opposite faces of the cube, because there are total 6 faces of the cube. So we have total three pair of opposite faces of the cube, and through these through the center of these 3 pairs of opposite faces, we have 3 different C2 axes of symmetry in the tetrahedral molecule. And each of these C2 axes of symmetry, if we see, produces only one symmetry operation, that is the C2 operation only, because if we do C2 2 times, that is a rotation of 360 degree, it is essentially identity operation. So there are 3 C2 axes of symmetry, and each of these C2 axes of symmetry produces one symmetry operation. So there are a total of 3 C2 symmetry operations present in the tetrahedral molecule. Now we are done with the proper axis of symmetry as well. There are no other proper axis of symmetry in case of the tetrahedron, and we will now try to see if there are improper axis of symmetry present in the tetrahedron. Now if we draw the tetrahedron once again in this fashion, and let's level also the hydrogen atoms, let us now do a C4 operation with respect to the axis which is collinear to this C2 axis of symmetry. In that case, what is going to happen, because these two pair of hydrogen atoms lie on the plane of the board, while these two pair of hydrogen atoms lie on a plane which is perpendicular to the plane of the board over here. So when we do rotation of 90 degree with respect to this axis, what is going to happen is that these two hydrogen atoms which initially lie on the plane of the board will now lie on a plane which is perpendicular to the plane of the board when we do this 90 degree rotation. Similarly, these two hydrogen atoms which lie on a plane perpendicular to the plane of the board will be placed on the plane of this board upon 90 degree rotation with respect to this axis. So the final configuration we can draw it as, when we do in this way, H1 and H2 is going to lie on plane perpendicular to the plane of the board, while H4 and H3 are going to lie on the plane of the board after 90 degree rotation. So what we see is that we reach a configuration which is distinguishable from the initial configuration. We can figure out that we have performed a movement of the molecule over here, and so this is not a symmetry operation, and we do not have a C4 axis of symmetry in case of the tetrahedral molecule. But now if we do reflection with respect to a plane perpendicular to this plane of to the axis with respect to which we did rotation operation, because we did rotation with respect to this particular axis, and if we do reflection with respect to a plane which is perpendicular to this axis, so when we do this reflection operation with respect to this plane over here, what is going to happen is that the top two hydrogens will occupy the bottom position over here, and the bottom two hydrogens will go to the top. So that means the final configuration that we are going to get, which H3 and H4 will go to the top over here, while H2 and H1 will be over here. So now if we compare this configuration with the initial configuration of the methane molecule over here, we will see that these are indistinguishable except for the level of the hydrogen atoms. So what we have done is that we have performed an S4 symmetry operation over here in case of the tetrahedron. So we have a S4 axis of symmetry, and this S4 axis of symmetry is collinear to the C2Y axis of symmetry. So as we have already seen that in case of the tetrahedron, we have three C2 axis of symmetry. And what we have found over here now is that an S4 axis of symmetry, which is collinear to one of the C2 axis of symmetry in tetrahedron. So this again should let us to think that maybe there are two other S4 axis of symmetry collinear to the other two C2 axis of symmetry in the tetrahedron. So once again, let us draw the cube and then try to visualize these S4 axis of symmetry. So if we do, this is, let's do rotation with respect to this axis of symmetry, which is collinear to the y-axis, to C4y, and then we will have the final configuration is going to be this is carbon. So when we do C4 rotation with respect to this axis over here, the H1, sorry, this is not going to be the configuration over here because the position of the hydrogen atoms are going to change now. So this is carbon atom. So when we do 90-degree rotation in clockwise manner with respect to this axis, the H1 atom will now reach the position, this particular position over here. So this is going to be the position of H1. Similarly, H4 will reach this position over here, and H2 will reach over here. This is H4, this is H2, and H3 will reach this particular position. This is H3. So this is how it is going to be. It is no longer indistinguishable from the initial configuration, because we can easily distinguish between the initial configuration and this particular configuration, as we have already said that there is no C4 axis of symmetry in the tetrahedral molecule, and this operation we have done now in order to find out the S4 axis of symmetry. So then let us do reflection with respect to this plane over here, which is perpendicular to the axis on which we did the rotation of 90 degree. So when we do sigma, what is going to happen? We can redraw the tetrahedron. So H2, which was here, will reach over here. This is H2. And then H4, which was here, will reach here. After doing reflection, H1 will be here, and H3 will be here. So let us place the carbon atom. Does not change position because it lies on the plane itself. So what we see that we reach an indistinguishable configuration after doing both C4 and sigma perpendicular to the C4 operation or C4 axis that we have taken. Now this is what we have done, a S4 symmetry operation, and what again we have seen is that this S4 axis is collinear to the C2 Y axis, and it also passes through the center of these two opposite faces of the cube. And as we have identified the three C2 axis of symmetry in case of the tetrahedral molecule, by this C2 axis of symmetry passes through the center of opposite faces in the cube in this way. So this is this was C2x and this was C2z, and collinear to these two C2 axis of symmetry also there are S4 axis of symmetry. So this is S4x, and then this we can label as S4z. Just to distinguish between these three S4 axes, we have used the x, y, and z references here, because we know that these axes are going to be collinear with the x, y, and z axis respectively. And so what we have found over here is that if we do rotation of 90 degree with respect to these axes, and then do reflection with respect to the plane perpendicular to this axis, then we will again reach indistinguishable configuration. And what you should do is you should draw the configuration for each of these movements here, for each of these axis, S4 axis of symmetry, both for S4x as well as for S4z, because we have now what we have done is only for S4y we have drawn the configuration that we obtained after doing the C4 as well as after doing the sigma. So you should do it for both S4x as well as for S4z. You should draw the configuration for after doing the C4 as well as after doing the sigma, and then you should see whether the final configuration that you obtain is indistinguishable from the initial configuration of the tetrahedron or not. As well as what you should do is you should also switch the order of the sigma as well as C4 operations and then see if the result is same or if the result is different if we switch the order of the reflection as well as the rotation operation when we perform the S4 operation essentially. So this essentially what we have done is we have found out 3 more elements of symmetry in the tetrahedral molecule. That is, we have found that there are 3 S4 axes of symmetry are present in the tetrahedral molecule. Now we should find out how many symmetry operations are generated by the S4 axis of symmetry, each of these S4 axis of symmetry. S44. So when we do S41, it is C41 sigma. So we cannot simplify it any further. So it is going to remain as S41. S42 is essentially C42 and sigma 2. Now C42, if we simplify, we will find that 2 into 2 pi by 4 rotation when we do. So it is essentially 2 pi by 2. So it is C2 180 degree rotation plus sigma 2 is going to be equal to identity. So finally we will be left with only C2 over here. And then when we do S43, this is C43 and then sigma 3. So this will remain as C43 sigma. So we will end up with S43 only. And S44 is C44 sigma 4. Both of these are equal to identity. So this is going to be equal to identity. So what we see is that there are 2 distinct symmetry operations generated by the S4 axis of symmetry, that is S41 and S43. As well as we should also note that S42 is equal to C2. So this tells us already that there is a C2 axis of symmetry which is collinear to the S4 axis of symmetry in case of the tetrahedron. Because we see that S42 is equal to C2, which is a symmetry operation generated by a C2 axis of symmetry. So we know also, even if we are not able to visualize the C2 axis of symmetry and only able to visualize the S4 axis of symmetry, when we simplify or when we find out the symmetry operations produced by the S4 axis of symmetry, we know that there is going to be a C2 axis collinear to the S4 axis of symmetry. So each of these S4 axis of symmetry now produces 2 symmetry operations, S41 and S42. So there are 3 S4 axis of symmetry. So that will give us total 6 S4 symmetry operations. So now we can count the total number of symmetry operations that we found for the tetrahedron. So 6 plus 8 is 14. 6 plus 8 is 14. 14 plus 3 is 17. 17 plus 6 is 23 operations. And now we have to add another operation as well to this, because the identity operation is always present in any molecule. The identity element is always present, because we have seen in several of these cases these symmetry elements as well produced the identity operation, and that is why along with these 23 symmetry operation we have to add the identity element. So that will one identity operation essentially. So now the total number of symmetry operations we found in the tetrahedron is equal to 24 symmetry operations. So we have now reduced all symmetry operation in the tetrahedral molecule. That is, there are 6 planes of symmetry, and all of these six planes of symmetry produces one symmetry operation, and there are total 6 symmetry operations. See, there are 4 C3 axes of symmetry. Each of them produces 2 symmetry operations. So total there are 8 C3 operations. There are 3 C2 axes of symmetry, and each of them produces again one symmetry operation. So there are 3 C2 operations. And finally we saw that there are also 3 S4 axes of symmetry, and each of these S4 axes of symmetry produces two symmetry operations, that is S4-1 and S4-3, and there are total 6 S4 symmetry operations. So we have now found out all the symmetry operations in the tetrahedral molecule. It is a very important exercise because in any molecule, in order to apply the principles of group theory in symmetry, we need to list all the symmetry operations that are present in the molecule, not the symmetry elements alone, but also the symmetry operations are very important so that we can apply the principles of group theory to this symmetry. In the next lecture, we will discuss about the symmetry operations that are present in an octahedral molecule. And this essentially brings us to the end of this lecture. And I thank you very much for being with me during this lecture.